Allison Transmission prides itself in developing quality products that meet and often exceed customer expectations. Allison also knows the importance of properly maintaining those products for long-term performance excellence. This program is designed to help maintenance technicians identify and solve driveline problems. Specifically, this program will show you how to isolate driveline vibrations from other types of vibrations and how to troubleshoot their cause. These procedures are appropriate for most drivelines. This program will also show you how to manually evaluate a driveline when checking driveline phasing and angularity. Following the manual evaluation information, there will also be an explanation of the driveline analysis software program, which gives you a much more complete and exacting driveline analysis. In this video, each segment will be followed by an exercise. When this stop tape sign appears, stop the VCR and refer to the question listed in your Driveline Troubleshooting Review booklet. You'll need a paper and pencil to write down your answers. The next segment will begin in a few seconds. Stop the tape and get the required materials if you don't already have them with you. When you're assigned a truck with a vibration problem, you should first ask the driver these questions. Where does the vibration come from? What does it sound like? Is it a constant sound or does it change? Can you sense the vibration through the steering column or the seat? At what speed does it occur? At what speed is it the worst? Is the vibration new or an old one getting worse? There are two types of vibrations the drivers commonly report. A low-frequency vibration, which is usually caused by a component turning at road speed, such as wheels, tires, brake drums, axle shafts, and wheel bearings. A driver may instead report a high-frequency vibration, such as a buzz or hum. This type of vibration may indicate a driveline problem, but not necessarily. So you'll need to perform tests to eliminate other potential causes for vibration. First, do an RPM test. Set the vehicle parking brake. Chock the wheels. Put the transmission in neutral and start the engine. Run the engine through its RPM range from idle to no load speed. If you detect a vibration during this test, the trouble is not in the driveline, but instead in the engine, torque converter, or transmission. If there is no vibration, then you should do a road speed test. To do a road speed test, drive the vehicle through the speed range where the vibration occurs. If you notice a low-frequency vibration, such as a shimmying or shaking, the cause is probably a wheel, tire or brake drum, axle shaft, or wheel bearing. A high-speed vibration, or buzz, indicates a possible driveline problem. Usually, a driveline vibration shows up at a specific speed range, for example, between 45 and 55 miles an hour. To be sure that the vibration is caused by the driveline, you need to perform a coast test. While driving the vehicle, accelerate through the vibration speed range. Shift to neutral and coast back through the vibration range. If the vibration recurs, the problem is probably in the driveline. To avoid damaging the transmission when you perform this test, brake the vehicle to below 25 miles an hour while maintaining RPM at about 1500 before shifting back into drive. The coast test is a troubleshooting procedure only and should not be done during normal operation of the vehicle, and in some areas it cannot be performed on public highways. To review the information in this section, when you're assigned a vehicle with a vibration problem, first ask your driver a series of questions. You'll find these listed in your review booklet. Then, if you think the problem could be with the drivetrain, there are several tests you can perform to isolate the problem. When the stop tape sign appears on the screen, you should stop the VCR and briefly write down what you do to eliminate the engine, torque converter, and transmission as possible sources of vibration. Then list how you'd eliminate wheel, tire, and brake drum balance problems as potential sources. Refer to Exercise 1 in your booklet for these questions. Refer to the section on isolating vibration for a review. When you've finished answering the questions, press play to restart the program. Please stop the tape now. Your answer for Exercise 1 should be: the first step in isolating a vibration problem is the RPM test. Vibrations that show up in this test are caused by engine, torque converter, or transmission problems. The road speed test helps eliminate wheels, tires, brake drums, axle shaft, or wheel bearing problems as vibration sources. And the high-speed coast test tells you it may be a driveline problem. When working with a new vehicle, or one that has been modified, it's important to consider the design of the driveline before further troubleshooting the cause of vibration. For information about the shaft length, wall thickness, tube size, and driveline speed, refer to your Sales Tech Data Book SA 1800. It's listed in Technical Document 111. There are 5 major areas of the driveline to check for a potential cause of vibration: the balance and/or runout, worn or damaged driveline components, U-joint phasing, driveline angularity, and driveline speed. As you know, any set of components that spin or rotate must be balanced for proper operation and to avoid vibration. It's especially critical for driveline components that are rotating at high speeds. Driveline troubleshooting should begin with an inspection of all the driveline components for possible causes of imbalance. Look for an uneven buildup of paint, undercoating, or mud that could throw the driveline out of balance. Also, check for missing shaft balance weights or damaged driveline components. Check the engine and transmission mounts to ensure the power package is still at the angle the truck manufacturer intended. Inspect the carrier bearing in the driveline to make sure it's not damaged and that it won't allow the shaft to travel in an elliptical pattern. Look at the driveline slip joint. Make sure it can move freely and has the proper amount of travel. Check the axle mounts and rear springs to make certain they're not loose or broken. Next, inspect the U-joints and replace any that are damaged or worn. Then, check the shaft runout or the position of the shaft around its operating center line. Remove all paint from a section in the center of the shaft and sections 3 inches from the yoke or spline weld at each end. Use a dial indicator to check runout 3 different positions along the shaft. Check the runout at each of these points in this manner. Attach the indicator to the frame. Zero the needle. Rotate the shaft and read the dial. A diagram that illustrates the allowable tolerances for these 3 measurements is included in the review booklet. If a shaft is beyond allowable tolerances, it should be replaced. In a few moments, the stop tape sign will appear. Refer to exercise number 2 in your review booklet regarding runout. Use the chart on runout tolerance to determine which of the runout readings indicates a runout problem. On this exercise, the readings which indicate a runout problem are number 2 and number 3. When you discover a potential runout problem, you'll look for a worn carrier bearing or a U-joint or a defective shaft. If the balance is proper and the runout is within acceptable tolerances and all components are in good working condition, the next driveline areas to check for a source of vibration are U-joint phasing and driveline angularity. To minimize vibration, the driveline must be correctly phased and have appropriate angles. Correct phasing of a driveline means that the yokes on either side of the driveline element must be in line or parallel. Angularity refers to the working angle of the U-joints. Smooth operation requires that these angles be the same or within acceptable tolerances for each element in the driveline. The working angles for each pair of U-joints should be the same. To find out why improper phasing and angularity cause vibration, let's look at this working model of a driveline. As you know, U-joints are designed to work at angles. And when you have a linked shaft, with each section rotating at a different angle, a unique phenomenon occurs, which we'll demonstrate with this model. The angles have been exaggerated to better demonstrate vibration. This model has an electric motor which rotates at a constant speed. As you can see from the white stripes, we've adjusted the yokes so that they're 90 degrees out of phase. When you look at the driveline model, you can see that the yokes are at right angles. Each shaft has a sprocket attached. When the driveline rotates, a card can be held next to the sprocket, and the sound will indicate variations in speed. For example, the first shaft from the motor rotates at a constant speed and sounds like this. The constant sound indicates constant speed. But listen to what happens when we hold the card to the sprocket on the second shaft. The rotating speed of the shaft varies. One revolution of the shaft sounds like this. As you can tell from the sound, the shaft speeds up and slows down twice. Now let's listen to the sprocket of the third shaft. The speed of the third shaft varies even more than the second. This is an out-of-phase condition. At high RPM, the varied speed of the third shaft will show up as vibration. For vibration-free operation, the last element in a driveline must rotate at a constant speed. Now, we'll put the yokes back in phase by lining them up. With the yokes parallel, listen to the speeds of each shaft. Again, the first shaft is rotating at a constant speed. Again, the second shaft rotates at a varied speed. But with the U-joints in phase, the third shaft rotates at a constant speed. By lining up the yokes on each shaft, we've canceled out the fluctuating speed of the center sprocket. This canceling effect only works if each U-joint is at the proper angle. In other words, proper phasing will only eliminate vibration if the driveline angles are correct. The angle of the U-joint at each end of the shaft should be the same. We can demonstrate this by changing the working angle of the first U-joint. Now, even though the driveline is in phase, we have a vibration condition. With a large amount of angle difference, the first shaft will rotate at a constant rate. And the second shaft will, as expected, rotate at a varied speed. But the third shaft also rotates at a varied speed. Drivelines must be in phase, and the U-joints adjusted to equal angles for vibration-free operation. When you begin troubleshooting, the first area to check is proper U-joint phasing. Visually check to make certain that the U-joints are parallel. Then use an inclinometer to measure the angle of each U-joint yoke. But first, clean the surface where you are measuring to make certain it is free from dirt and burrs. Place the inclinometer on the surface of one U-joint and read the angle. Take the reading of the second angle and compare the two. Normal phasing tolerance range is 5 degrees. However, if your readings vary, check the manufacturer's specs to see if the difference is within tolerance. Repeat this procedure for each shaft of the driveline. For this exercise on U-joint phasing, refer to Exercise 3 in your booklet. Here are 3 sets of readings. Using the section on phasing as a reference, determine which of the U-joint readings indicates an out-of-phase condition. Restart the program when you're finished. If you concluded that the third set of readings shows an out-of-phase condition, you are correct. The first and second readings are within tolerance. To correct an out-of-phase condition, disconnect the U-joint and separate the shaft from the slip joint. Then realign the shaft so that the U-joint yokes are in phase or parallel. Take a second set of readings to make sure you've corrected the problem. Once you are certain the driveline is in phase, the next step is to check the angularity of the driveline. First, you need to measure the angles of all the U-joints, then compute the angularity to determine if it's within tolerance. Angularity may have to be checked on the vehicle in both a loaded and unloaded condition. But first, let's discuss installed and working angles and how to measure them. The working angle of a U-joint is the angle of one U-joint yoke, or the shaft connected to the U-joint, in relation to the other yoke or shaft. Imagine 2 lines perpendicular to each yoke. Where those lines meet, they form the working angle. An installed angle is the angle at which the driveline element is installed. It is the angle between a horizontal line and the driveline element, as shown here. You can figure out the working angle of a particular U-joint by using the installed angles of the driveline elements that meet in the U-joint, then compute the angularity. Before taking each reading, clean off spots on each element. Then begin with the angle of the transmission. Use an inclinometer to determine the installed angle of each driveline element, starting with the transmission and working toward the rear. Then, draw a line to represent the element you've measured and write the reading down, designating positive or negative depending upon its position. This is a 5-degree reading, and it's positive. If a driveline element points down, it is positive. One that points up is negative. Next, you're ready to compute the working angles. Keep in mind that each U-joint pair should have the same working angle. Compute the working angles by adding or subtracting the element readings depending on the sign. If the signs are the same, subtract the smaller from the larger. If the signs are different, add the 2 numbers. In this example, the elements on the left both have negative signs, so you subtract. If they had been positive, you would have also subtracted. The elements on the right have different signs, so you add. The final exercise in this program involves computing the working angles of a driveline using the example shown here. It's also listed under Exercise 4 in your booklet. For review, refer to the booklet section labeled Computing Angularity. When you've finished, restart the program. The working angles of these U-joints are 5 degrees and 5.5 degrees. As you know, each pair of angles should be the same or within acceptable tolerances. And the tolerance for shafts that turn at 3200 RPM or higher is 1/2 a degree. Tolerances for shafts turning below speeds of 3200 RPM is 1 degree. When computing angularity for a driveline with an odd number of U-joints, the extra U-joint should have a working angle no greater than 1/2 of a degree at speeds of 3200 RPM or more, and the angle must be no greater than 1 degree at speeds below 3200 RPM. The maximum allowable working angle of a U-joint is determined by top RPM. Your review booklet lists maximum working angles for specific RPM ranges. Each pair of angles, besides being equal, must also be within maximum RPM limitations. When you discover an angularity problem, refer the problem to the vehicle manufacturer or driveline specialist. The manufacturer might install shims between the springs and the axle housing to adjust the rear axle pinion angle, or correct the angle by adjusting a tie rod. Once an angularity problem has been solved, take a second set of readings to make sure the angles are within acceptable tolerances. Once the vehicle has been repaired and you're certain the driveline has proper balance and runout and the U-joints are in proper phase and have acceptable angularity, take the vehicle for another road test. Then perform the coast test again, remembering to brake to below 25 miles an hour and maintain RPM at approximately 1500 before shifting back into drive. You should find that the vibration has been eliminated. The key to efficient driveline maintenance is a systematic troubleshooting approach. When you're assigned a truck with a problem, isolate the vibration by first asking the driver a series of questions. Then, you'll need to perform the tests listed here to eliminate other potential sources of the vibration. If you think the cause of the vibration is in the driveline, begin troubleshooting with a check of the driveline balance. Then, inspect the components and U-joints and replace any that are damaged or worn. Check the runout, the U-joint phasing, and finally, the angularity. And don't forget to follow up repairs to make certain the vibration problem has been solved. If you have access to the Driveline Analysis software program, it provides a more comprehensive and accurate analysis of a driveline. To use this program, you must first measure the driveline phasing and angularity. This is done by following the procedures shown previously in this tape. Now, the prop shaft lengths need to be measured. To accurately determine the length of the front prop shaft, measure between the centers of each U-joint. The same holds true for the rear prop shaft. Take your measurements from the U-joint centers. Driveline offset is the next measurement you'll need. This checks the prop shaft's position between the vehicle's frame rails. Tie a plumb bob to the frame rail and use it as a reference point. Measure from the plumb bob string to the center of each U-joint and record your measurements. Finally, you'll need to determine what the maximum driveline speed will be based on maximum engine RPM and the highest transmission gear ratio. Locate the engine data tag on the engine valve cover or block. The tag will list the engine's high idle RPM, also referred to as no load RPM. To determine maximum driveline speed, divide no load RPM by the transmission's highest gear ratio. Now you're ready to enter all this information into the Installation Design Calculation software. This program is run on an IBM-compatible PC. From the main menu, Multiple Joint Driveline Analysis is selected. This brings a series of questions on screen that lead you through the analysis process. The computer asks a series of questions based on vehicle specifications and your driveline measurements. You'll enter the number of U-joints in the drive shaft, the transmission's maximum output RPM based on maximum engine speed, the transmission and pinion vertical slope, the transmission and pinion horizontal slope, which in this case is 0, each shaft's slope, U-joint offset measurements, prop shaft lengths, and difference in U-joint phasing, if any. When finished, the software summarizes your inputs and calculates results. These results include torsional acceleration, drive U-joint inertial acceleration, and coast U-joint inertial acceleration. Each acceleration is labeled either OK for acceptable or XXX for unacceptable. To better understand the software's calculations, let's take a closer look at what these terms mean. As driveline U-joints rotate, they speed up and slow down. This is an inherent design characteristic of all U-joints. During one complete driveline revolution, each U-joint will speed up and slow down twice. Inertial acceleration measures a U-joint's speed variance during one revolution of the drive shaft. Too much variance can cause U-joint damage. The U-joint must be within inertial acceleration limits. Torsional acceleration expresses the driveline's ability to absorb each U-joint's change in speed. U-joint phasing and angularity is critical to torsional acceleration. As the front U-joint changes speed, the next U-joint must be phased to absorb the change. Then, the next U-joint must absorb that U-joint's changes, and so on. Torsional acceleration is the final result of all U-joint accelerations as they add up or cancel each other. If torsional acceleration is beyond specified limits, vibrations can occur. Sometimes these vibrations can be felt by the vehicle operator, and other times they can't. Even though the vibrations aren't felt, they can still cause transmission or axle damage. That's why the software's calculations are so important. Trouble may exist without drivability problems. The software lists torsional acceleration limits first, then shows inertial acceleration limits for the front or drive U-joint, and finally inertial acceleration for the pinion or coast U-joint. If any limits are unacceptable, double-check your measurements and calculations, and, if necessary, refer the vehicle to a driveline specialist. In addition to the material that's been presented in this program, your review booklet is also a good source for driveline troubleshooting procedures. Thank you for sharing in Allison's customer commitment to quality products. Your expertise in driveline troubleshooting is essential to keeping our transmissions running smoothly and efficiently.